Hello, this is Dr. Eddie Morgan over at Clovis East High School. I want to walk through the Unit 8 review with you, and hopefully this will help you for the upcoming test. The first question is, what is a rigid motion? A rigid motion is a transformation in the plane that preserves distance and angle measures. That simply means that the size, the length, and the angles don't change distance. The sides are the same length and the angles are the same measure. We've been studying three types of rigid motion: a translation, a rotation, and even a reflection. And in each of those cases, it doesn't change size. Think of a rigid motion as having like a box or something it's metal or it's wood. It stays the size. You can move it around, you can turn it upside down, you can throw it across the room, but it stays the same size. And that's what a rigid motion translation is. Problem number 2 asks us to name the transformation that's occurring between those two trapezoids. If you notice the blue lines that I've drawn, you can see that the figure is simply being rotated counterclockwise 90 degrees. That's the transformation that's occurring. It's a rotation. Is it a rigid motion? Yes. You'll notice that the two shapes have the same size, the sides are the same length, and the angles are the same measure. So that is considered a rigid motion. You want to remember this phrase: it preserves distance and angle measures. You can use that phrase at least twice on the test to answer questions about, does it change size, is it rigid motion? So try to remember that phrase: it preserves distance and angle measures. Problems 3 through 8 ask us to describe the transformation represented by the coordinate notation. If you notice the first one, xy becomes x minus y. So if you think about that on a scale, what's happening is that the x stays the same, but the y flips. And so this is what would be if we're crossing the x-axis. You notice like point A is negative 1, 2, negative 3, but A prime is also negative 3. All that happens is the y flips across the x-axis. So that is a reflection across the x-axis. A reflection across the y-axis, interestingly, the y stays the same, but the x would change. In number 4, you notice that x stays the same, but y goes down 1. Y negative 1 means I'm going to go down 1. So what I have is a translation down 1. You notice the triangle just shifts down 1. The x's stay the same, but the y's go down 1. On the next one, we do the same thing, but with the x. Notice the x changes by adding 2, which means I'm going to shift 2 to the right, but y stays the same. So this is a shift of the triangle 2 to the right. In number 6, we have an interesting thing where x and y actually change places and one becomes negative. This is actually the rotation 90 degrees clockwise. If you were to look at point A in the original triangle is 2, 3, but then when you rotate it, it becomes negative 3, 2. And that's the nature of the negative yx. By the way, if you get y negative x, that's a full 270 or 90 degrees going the other direction. Number 7 is kind of easy to remember. You notice that both x and y both become opposites. And that's kind of like reflecting it over the x-axis and then reflecting it over the y. What you have here is this is the total counterclockwise. If you take it and go 180 degrees, you'll see that 2, 3 becomes negative 2, negative 3. And so the negative x, negative y is a 180 degree. And finally, number 8 is just a translation where we have x minus 2, which means I go 2 to the left, y plus 3, which means I go 3 up, and so it looks kind of like that: 2 to the left and 3 up. Problem 9 asks us to name 3 transformations that will map the shape onto itself. There's a lot of them here because this is a square. I think on the test you'll get a rectangle, so there won't be quite as many, but a square, there's lots of ways you can turn and reflect and move this to get the same thing. First thing I notice is that I can simply do a rotation. If I rotate this square 90 degrees, I still have a square. In fact, I can do it again. I can rotate it 180 degrees and get a square, or 270 3/4 and get a square, or I could go all the way around 360 and come back to where I was. So you can do a rotation. Likewise, I can do some reflections. If I choose the x-axis, notice I can reflip. I'm just turning the square upside down. I get the same thing. I can also do it on the y-axis, left to right, and just flip it from one side to the other, and then even diagonally. unique because it's a square. Notice if I flip it diagonally, I still get a square, and I can use the y equal x line. I can also use the y equal minus x line. So there's a lot of ways that I can map this one onto itself. It's unique because it's a square. The more different the shape is, the less of these are available. Number 10 says that triangle ABC has been rotated 90 degrees clockwise about the origin. Name all of the sides, angles, and sides. Well, so this is what I've got. I've got a 90-degree rotation. First thing I notice, if I want to just check myself, I'm just going to notice that when I shift it, A becomes T, B shifts over to R, and C shifts over to 0. If you can ever write this triangle ABC maps on a triangle TRO, these problems become very easy, because you can actually look at these three letters and compare the other three letters and look where they're placed and find your answers. For example, A matches angle T. They're both the first letter in the triangles here, if I've done it right. B becomes R, and C becomes O. Okay? Or you can just look at the diagram and see how did they go there. And then likewise, using these, you can put all the segments together, because obviously AB are the first two letters in the triangle, TR are the first two letters in the second triangle. Likewise, BC and RO, and then CA and OT. So just a note in helping you, if you can set up this first statement, triangle ABC maps onto triangle TRO in the beginning, you can actually answer all the other 6 just from looking at that diagram. In problem 11, we're asked to look at the quadrilateral play, PLAY, and it says it's translated up 5 units and left 8 units. What are the coordinates of P? Well, if I look here and just P and just use it, if I go up 5 and over 8, you see it's off the graph. So I either need a bigger piece of graph paper, or I may just want to use the coordinate notation. Notice here in the coordinate notation that up is the y-axis, so it's going to be y plus 5. Left 8 means x minus 8. So if I put in my point here, -3, 0, and so -3 minus 8 and 0 plus 5, I'll end up with that P prime is -11, 5, which looks appropriate even though I can't see it on my graph. In the next one, number 12, it says if play is reflected across the y-axis, what are the coordinates of L prime and y prime? Well, let's draw the y-axis. It looks like that. And so I'm going to reflect. If I look at point L first, it goes over 1 to the y-axis, so I go 1 more, so that's going to be my point there. It looks like 1, -5. If we check it out, a reflection says that the x flips, but the y stays the same, just like our diagram shows. So -1, 5, if you take the opposite of -1, you end up with 1, -5, which matches what we see on our graph. We look at y prime's on the right side, so if I go back 5 to the y-axis and then 5 over the other side, you see I'm going to be at -5, 1. Let's check it out with our coordinate notation. So 5, -1, take the x and take the opposite, and we end up with -5, 1, which matches what we see on the graph. Problem 13 says that if our figure play is rotated 90 degrees counterclockwise about the origin, what are the coordinates of A prime and L prime? You could do this with patty paper. You could set your patty paper down, mark your figure, put a cross through the origin, and then put your pencil on the origin and turn your paper 90 degrees and try to figure it out. I find it just as easy to use the formula that xy becomes -yx. Notice the x and the y change places, and then the first coordinate becomes the opposite. So if I put in the point A, 4, -5, first thing I do, switch them, -5, 4, and then the opposite of -5 is +5, so A prime would be 5, 4. For L, same thing. L is -1, -5, so first switch them, -5, -1, then the opposite of the first one, -5, is +5, and the answer is 5, -1. Problem 14 asks us to, interesting question, it wants us to find the slope of P prime Y prime if it's reflected across the x-axis. You might look at PY right now and realize it goes down 1 and over 8, so the slope is -1/8. But what happens if I reflect that across the x-axis? Well, let's find out what P prime and Y prime are. P, by the way, is -3, 0. Notice that it's actually on the x-axis, so it doesn't change when you reflect it. On the other hand, y prime, remember we're changing the y, so 5 minus 1 becomes 5 plus 1. So now let's find the slope. Remember that the slope is simply going to be the change in y, the rise, over the change in x, the run, or another way of saying it, y2 minus y1 over x2 minus x1. So in this case, y2 minus y1 is 1 minus 0, and x2 minus x1 is 5 minus minus 3. Now don't forget that subtracting a negative becomes adding the opposite, or so it becomes 5 plus 3. So our answer is 1 over 8. The interesting thing is that the original one was minus 1/8. When I reflect it over the x-axis, it becomes the opposite, or 1/8. Not perpendicular, just the opposite. 15 says if the figure is rotated 270 degrees counterclockwise about the origin, what will the slope be? Well, in this case, once again, let's figure out what the points are going to be. xy becomes y minus x, so they switch and the x changes. So A, the point A, 4 minus 5, if I turn them around, I get minus 5, 4, and then I'm going to switch the 4 to minus 4, so I end up with negative 5, negative 4. Y, on the other hand, switch them first, minus y, 5, and then the second one becomes negative, so negative 1, negative 5, and now we just simply do the slope. So the slope here is going to be y2 minus y1 minus 4 minus 5 minus minus 4. Remember, that'll be minus 5 plus 4. And then minus 1 minus minus 5, or minus 1 plus 5. And we end up with negative 1/4. Okay? So the slope of that is negative 1/4. Find y prime if it's translated using this rule. In this case, here's our rule. So I just simply plug in y prime. Y is 5, negative 1, so 5 minus 7, and y plus 2 is going to end up with negative 2, 1. Number 17 says find a prime if play is rotated using this rule. And so in this case, using this rule, which is actually a 90-degree turn, I put in the point 4 minus 5, so we switch them around and we get minus 5, 4, and then we take the opposite of the y, so minus minus 5, and we end up with 5, 4 as our answer. Number 18, what happens if I rotated 180 degrees around the origin? Well, a rotation is will it be congruent? I mean, a rotation changes xy becomes minus x minus y. But the question is it going to be congruent? And the answer is yes, because it's a rotation is a rigid motion transformation. And that means it preserves distance and angle measures. And so the figure PLAY is going to be congruent to P prime, L prime, A prime, Y prime. This is one of those questions you get on the test where they ask, you know, if I make this translation or this rotation as a reflection, is it going to be congruent? And the answer is yes, because it's a rigid motion. It preserves distance and angle measures. Just got to remember that phrase. For problems 19 and 20, they ask us to describe the transformation and write it in coordinate notation. In both cases, we're going from the dotted figure to the solid figure. The first one, as I look at there, I'm saying, how can I get the dotted at least oriented? And maybe I can orient it one way and then translate it that direction. So I realize that I can do that by reflecting it across the x-axis. So I draw my x-axis and then start reflecting the points. 4 down there, and then 4 down, and then 5 down, 5 down. And notice now I have the red triangle is in the same orientation as the black one. So the first part of my coordinate notation is my xy is going to become x minus y. Second part, now I just simply need to translate it for right. Now what I'm going to do with the coordinate notation, I'm going to use the first one and now simply add the 4 to the x. So you see I get xy equals x plus 4 minus y, and that notation combines both the reflection and the translation. On the second one, I look at it and notice, now how can I take the dotted and orient it? And I realize that if I translate it 90 degrees clockwise, which would be 270 counterclockwise, I can get in that shape. So let's do the translation. And that's the rotation. And that is xy goes to y minus x. Now you notice all I need to do is translate it 1 left and 5 up. It's a little tricky here. Remember that when you go to the 1 left, that's going to be the x coordinate minus 1, but right now y's in that thing. So notice when I write my final, it's y minus 1 and negative x plus 5, and that becomes the answer of that composition of those two transpositions. For the last problems, we're going to do constructions. In order to do constructions, you're going to need to get your ruler and your compass, and we're going to construct different angles and segments and parallel lines and perpendicular lines, etc. So let's get started. First, we want to make a copy of angle A. So the first thing we're going to do is draw a ray with an end and give point. So go down below here and draw a line. Okay? You can put a point on the end of it. That's going to be your end point there. All right. Now, second, we're going to, with the compass on the vertex, and there's the vertex there, we're going to draw an arc that intersects the given angle. So from there, we're going to reach up with our compass and draw an arc across here, like so. Okay. At this point, without changing the setting, because we want it to be the exact same arc, we're going to come down to here to this vertex, put our compass on that point, and then come over here and draw the exact same arc. So the arcs are exactly the same. Now the next point is we're going to measure the arc. So what I'm going to do here, I'm going to open the compass to the length of the original arc. So I come up here and I put the end of the arc here and then open it up so that I get it exactly how far is it from there to there. And I can mark a little arc there to show that. And then at this point, I come down with the exact same setting. I come down at this point and do it again. All right. So I get that kind of look there. And you'll notice now that the distance from here to here is exactly the same for both of them. So all I need to do now is draw a line from the vertex through the point of the intersection. And I now have, in problem 22, we're being asked to copy XY right here and can then construct its perpendicular bisector right down the middle here. So the first step, we need to start by drawing a line, a ray with a given endpoint. I'll draw it down below here, and that's my starting point. I label one side A prime. That's going to be the length. I'm going to make it AB. So by second point, let's open the compass to the length of our original segment. So come up and put your segment on X, and then open it up to find how far is it from X to Y. Make a little mark there, indicates that's the length from X to Y. Now, without changing the compass setting, come down and put it on A, and then reach out and draw the same arc on this ray. Notice that the red arcs are exactly the same. And then at this point, I can put in the point, and I'll label that B prime, and now you notice that the distance from X to Y is the same as the distance from A to B. Okay? So we've copied XY. That's the first step. Second step, let's draw the perpendicular bisector. All right? So we put the compass on either end of here. I'm going to start with B, and I'm going to reach out. My arc just has to be bigger than half, and you'll see why in a minute. If it's not half, they won't intersect. So I'm going to reach out my arc out here and make a big arc like that. Okay? And then without changing the setting, I'm going to move my compass over to A and then draw the exact same arc going the other way, like this. Okay? And now you notice that they intersect at the top and the bottom. If you will take your ruler and draw a line from that intersection to that intersection, straight line this way, that is your problem 22. We're being asked to construct a perpendicular line to the segment AB through point P. So what we're looking at is, here's our line AB, and we want to, from P, we want to draw a line that goes exactly, intersects here, but exactly at a perpendicular angle. So first thing we're going to do is, from the point P, we're going to draw 2 points on the line that are the same distance from the given point. In other words, the easiest way to do that is to open our compass and draw an arc from P that's going to cut the line at 2 places, and they'll both be the same distance. Notice that the distance from here to here and here to here are exactly the same. Next, we're going to open our compass and draw an arc from one of these points. Let's say this point here, and I'm going to draw an arc out this direction, and then keep the compass at the same length, I'm going to come over to the other equal point and draw it back this direction. So those 2 points are the same distance from these 2 points. And now finally then, if I go to line P and draw a line, in problem 24, we're being asked to construct a line through point Y that is parallel. So this time, here's the line, here's Y, so we're looking to draw a line that is exactly parallel to that line. And the key to this one involves creating two congruent angles. So let's get started. First, we want to draw a line from point Y to any of the points on the line. Okay, so I'm going to draw a line right there from Y to M. And now what I want to do is create an angle here, up here on Y, and that'll give me my line, my parallel line. So with the compass of the vertex here on M, I'm going to draw an arc, any arc, along here that I'm going to use to measure. So there's my arc. Now, just like before when we copied an angle, I'm going to move up now with the same compass setting. I'm going to go up to point Y and draw exactly the same arc. So the red arcs are the same. Okay? And now we simply have to measure this angle M and put it up on NY. So put your compass now on point M and then open it up and measure from here to here. Okay, so from the top here in the red line, I measure across to get the blue arc. Now that's the angle of my measure there. So I just come up here to above Y and measure the same distance here. And now if I copy a line from Y through the intersection, that turns out to be my parallel line. And so the blue line here is parallel. In number 24, we're being asked to construct a line through point Y that is perpendicular to M. So we've done this before where the point was up here and we drew one. Now we want to draw a perpendicular from this point that goes through Y and is perpendicular right at that point. So our first step we're going to do is construct 2 points on the line that are equal distance from the given point. And the easiest way to do that is put my compass on Y and open it up, and just kind of like I could draw a circle if I wanted to, but I'm just going to draw one side and the other side, but they're going to be exactly the same length. Okay? As I said, you can make a little circle there, but we're only interested in, on the line, 2 points that are equal distance. At this point then, we're going to open the arc a little wider, and we're going to draw an arc from one of these points above here, and we'll come over and do it here as well. But let's start here. We start at this point and draw an arc this way, and then you come over to the other side and draw the exact same arc from here up to here, and those 2 points are equal distance. And now all we have to do is draw a line from our point through that point, and that is our perpendicular. In problem 25, we're being asked to construct a triangle with these 3 sides. Here's my small side, my middle side, and my long side. So the first point I'm going to do, I need to start a beginning point. So like we have before, I'm going to draw a ray with a point on it. Okay, so that's going to be the bottom. And I'm going to start by using the largest segment. So I'm going to come up here and put my compass on this point and then measure across to that point. That gives me the length of my largest one. So now I'm going to come down next with the same compass setting. I'll come down and put it on the vertex of the ray and reach out here and mark out what exactly is the distance of that segment. All right. So if I can label that, that's 1 point there. Now we'll do the same thing with the middle segment. Come up here to the middle segment, put your compass right there, reach across and measure this length here. So there's the length of that middle one. And now you can choose either point. I chose the left point. I'm going to bring the compass down the same setting and put it on the vertex and just mark an arc out here, the length of the middle segment. Okay, so we put it here and then reach out and make the arc. So this is my long segment, this is my middle segment. So now let's do the same thing with the small one. We're going to open our compass at the end of the small one, reach across and measure it here. Put a little mark there. And now come down to the other end of your triangle, which is over here, and then reach out and mark it that distance. And so notice here is the large segment, here's the medium segment, and here's the small segment. And where they intersect is the point where those two have exactly the same length. So at this point, this is the third point. So we can now draw a line from here to here and from here to here, and we've now completed our triangle. In problem 26, they ask us to construct a rectangle with the two sides that are given there. All right, they want to take the rectangle to have this two sides and these two sides. So just like before, we're going to start by drawing an array and constructing the larger segment. So I put my point down there, and then I'm going to reach up here, and from this point to this point, I'm going to measure that angle, that segment. So I put a point here, come up here, and then I'm going to measure my segment from there to there, and then I'm going to bring that down, put my vertex here and reach across so that I get exactly the same angle, and I can put a dot there. So all I've done here is construct exactly this segment, the large segment. Well, we could just start like the triangle and measure the middle, but we need a rectangle, so we need some perpendicular lines here. So our next step is to construct a perpendicular line in each endpoint. And if you remember how we do this, the first thing we do is we're going to draw an equal distance on each side. So from that point, I draw there and there. Like I said, it's like a whole circle, but you just want them to be both the same length. And then open your compass a little bigger, and from each point, draw an angle up here, and then come over here and draw the same angle there and there, and now draw the line from here through the intersection, and I've done a perpendicular. And now we repeat the process over on the other one. So first we draw our arcs on both sides of the point there and there, and then open it up a little bit and reach up here and draw an arcs above and below here, and then draw the line through it, and we have two perpendicular lines. So we have one side and two right angles here. So all we have left now is to construct the smaller segment on each of these perpendiculars. So move up here, and we're going to measure from here to here. So you just have to reach out there and draw the length, and then come down on each point, put the point here and reach up and find out how far is there that smaller segment. So you get one there, come over the other one and do it again. You get one there and mark them, and now we have the 4 points of the rectangle. Okay, all we have to do now is connect these lines. Problem 27 is interesting because they want us to construct a 45-degree angle and a 22.5-degree angle. The key to this problem is to realize that 22.5 is half of 45, and then to realize, well, what 45 is half of a 90. So our pattern here is we're going to have to draw a line. First we're going to draw a 90-degree line, which is our perpendicular, and then we're going to bisect it twice. Okay, so let's start by drawing a perpendicular line. So first thing I want to do is simply just draw a line to get started with, any place, and then I can just pick a point on the line, and I'm going to draw my perpendicular bisector. Remember how we do that? From this line we draw, open the compass and draw like a circle, but we just want to mark two sides that are equal distance. Okay, and then open the compass a little wider and go to either point, like here, and reach up and draw a line, and then come over here and draw a line, two equal distance points, and then the line from the intersection through our point is our perpendicular, and what we form there now is a 90-degree angle. So to construct a 45-degree angle, our next step is to bisect that angle. So we're going to bisect that angle. So we're going to open our compass, and we're going to draw an arc using this angle. We're going to draw an arc across here to just show where the angle is. And now you can actually use on this one, you can use the same compass setting. You don't have to, but you're going to go to one of the sides here and reach out and draw an arc that direction. And then without changing the compass setting, come over the other side and draw it this direction. And now the point where they intersect, the line from there to the vertex, is our angle bisector. And what we've created is a 45-degree angle here and a 45-degree angle here. We've cut the 90-degree angle in half. So the last part is to draw a 22.5 angle. Well, all you have to do there is do the same thing for this angle here, this smaller angle. I can actually just use the same 2 points here, I don't have to draw them again, and take my angle here and reach out from here and draw an angle there, and then come over to this point here and draw the same angle there, arc there. And once again, a line from here to here is the bisector of the 45-degree angle, and now this angle and this angle are 22.5 degrees.